Okay, guys, today we're just going to do kind of an intro to some of the types of acid-base calculations you're going to need to know. And we're going to get into some theory that'll kind of maybe hopefully make some sense of everything that's going on. But before you watch the rest of this video, you should complete the Intro to Unit 5 assignment. So read through the notes and answer those questions. And if you feel comfortable with those kinds of questions, then you're in good shape to watch this video. If not, the video might be a little bit over your head, but again, we're just gonna take it one step at a time. All right, so we should kind of have a basic idea of what an acid is and what a base is, okay? And we know we have different theories, okay? So the different acid-base theories, you have your Arrhenius acid-base theory, you have your Bronsted-Lowry acid-base theory, and you have your Lewis acid-base theory. Okay, so if I ask you what an acid is, it really depends on what my definition is. Are we talking about an Arrhenius acid? Are we talking about a Bronsted-Lowry acid? Are we talking about a Lewis acid? And if I ask you what a base is, it's the same thing. This lesson isn't going to talk about differentiating what an acid is and what a base is. What we're going to focus on is water-based solutions and if they're acidic or basic, right? So aqueous solutions, all right? Things dissolve in water and they make the solution acidic or they make the solution basic. Or maybe the solution remains neutral, right? Pure water is neutral, so if we add something that makes it acidic, that would be an acid, right? If I add something to pure water and it makes the resulting solution basic, that would be a base. And if I add something to solution and to water and it makes the solution still have a neutral pH, then that thing's neutral and it's not an acid or a base, right? So now we're going to just focus on an acid is something that when I add it to water, it makes the solution acidic, which means an acidic solution means the pH is less than 7, okay? Or the pOH is greater than 7, depending on what you're measuring, right? But usually we go on the pH scale, not the pOH scale. So 7 is neutral, anything less than 7 for the pH is acidic, and anything above 7 would be basic. So really, an acid, what we want to think about when we're doing calculations, it's really just going, hey, what's the pH of this solution? What's the pH of this solution? Maybe what's the pOH of this solution? Or what is the H plus concentration in this water-based solution? Or what is the hydroxide ion concentration in this water-based solution? Okay, so those are the types of calculations we want to be able to do. All right. So instead of, saying, hey, this acid is an Arrhenius acid, and this acid is a Bronsted-Lowry acid, or this acid is a Lewis acid, or it's all three. Really, we're talking about when we, so we can answer questions about the theory and say, yeah, in this equation, that's a Bronsted-Lowry acid, but in this equation, it's an Arrhenius acid, but in this equation, it's a Lewis acid, whatever. Okay. We can differentiate between the theory. But when it comes down to calculations, we have water-based solutions, and that's all we're going to focus on, stuff dissolved in water, and we want to figure out what the pH of that solution is going to be. So is it going to be an acidic solution? Is it going to be a basic solution? Or is it going to be neutral? That's what we're trying to figure out, right? Okay? So let's understand. Water is always at equilibrium with itself. So what does that really mean? Okay, so any water-based solution, any aqueous solution, this thing is true. Kw equals 1 times 10 to the negative 14. Now, all of this stuff that we're about to go over is true when we're at 25 degrees Celsius. So Kw is this number, 1 times 10 to the negative 14, at 25 degrees Celsius. And just like any other equilibrium constant, that's all this is. It's a specific reaction, okay? But all this is a equilibrium constant. And we know that if temperature changes, this number would change. And if this number changes, then all of our calculations kind of change a little bit. So all of our acid-base calculation questions what's the pH of this solution, what's the pH of that solution, what's the hydronium concentration, what's the hydroxide concentration. All those calculations we're going to have to do. We're always assuming 25 degrees Celsius. Now, we should understand that kW changes as temperature changes, and we should know what the change is, meaning kW is an endothermic reaction, so kW is going to increase as temperature increases. And what does that do to pH? We should kind of understand that, which we'll talk about another time, okay? But any time we're calculating the pH of a solution, we're going to assume it's 25 degrees Celsius, so this is true, okay? All right, so this process is reaching equilibrium in water. So if you have pure water, this is happening, okay? But if you have other stuff added to water, this process right here described, this is the autoionization of water, has to come to equilibrium. And there's two ways to represent it. You can show it where one water molecule disassociates and forms an H plus and an OH minus, okay? Thinking maybe more like water as a salt, and it's breaking up into its individual ions, H plus and OH minus. But another way to think about the same thing is you could have two water molecules, and it's kind of illustrated here, one water molecule, another water molecule, or you could just say two water molecules. And what happens is one of the water molecules, when it bumps into another water molecule, will lose an H plus to it. So the water molecule that gains an H plus will become hydronium, and the water molecule that lost an H plus will become hydroxide. And so in acid-base chemistry, you need to understand that H plus, hydrogen ions, and hydronium ions, H3O plus, they're synonymous with each other. So an acid is something that produces H plus in solution, but you could also say an acid is something that produces hydronium in solution, right? And a base is something that produces hydroxide. But regardless, let's just think of pure water. This is happening in pure water, and this process reaches an equilibrium. And that equilibrium is the equilibrium position of this reaction. And again, all three of these is the same thing. The equilibrium position of this reaction is what kW is. kW is 1 times 10 to the negative 14. So we know the equilibrium constant for this reaction is 1 times 10 to the negative 14. What does that really mean? It means that in pure water, we have mostly H2O liquid molecules, right? In pure water, we don't have a lot of H plus and we don't have a lot of OH minus. And that's a good thing, right? Because we know H plus and OH minus can do some damage. But when we drink pure water, we don't really have to worry about the H plus and OH minus because it's not highly concentrated. It's going to be really small because the equilibrium constant for this is really small, okay? All right, and let's figure out what those concentrations are. Now that we know the kW for this reaction, let's figure out what the equilibrium concentrations of these are in pure water, okay? So we could make a rice chart with that equation, right? We don't care about the liquid water. It's not a part of our equilibrium expression. And notice that if it's pure water, the amount of H plus is going to be equal to the amount of OH minus at equilibrium. The kW expression, right, if this is my reaction, it would just be the concentration of this times the concentration of that over the reactants, but the reactants is only liquid, so we won't include that. So kW is just equal to the concentration of H plus times the concentration of OH minus. Now again, because hydronium is synonymous with H plus, you could replace this with H3O plus. It's the same thing, all right? And we know what that number is equal to. At 25 degrees Celsius, we know that this is equal to 1 times 10 to the negative 14, all right? And we know that if it's just pure water, if that's all we start out with, then the amount of H plus and the amount of OH minus are going to be equal, so that would be X times X, so X squared. And so if we solve for X, if we just take the square root of that, okay, we get the molarity of H plus in pure water at equilibrium, and we get the molarity of OH minus. Notice they're equal, okay? And the product of those two equals kW, 1 times 10 to the negative 14. So H plus concentration times OH minus concentration, and again, you could replace that with hydronium. H plus times OH minus always equals 1 times 10 to the negative 14, okay? And what is pH? pH is the negative log of H plus concentration. So if we take the negative log of this, that's 7. And so that's how we get the fact that pure water is neutral, and we're defining neutral as a pH of 7 because the concentration of H plus in pure water is 1 times 10 to the negative 7. And pH is just a measurement of the negative log of the molarity of H plus. So if the molarity of H plus is 1 times 10 to the negative 7 in pure water, then the negative log of that is 7. And that's where we get pH is 7, right? But also the pOH is also 7, okay? So pOH is just the negative log of the OH minus concentration. And since they're equal, in pure water, the pH of pure water is 7, the pOH of pure water is also 7. And remember, pH plus pOH at 25 degrees Celsius should always equal to 14, right? And so it makes sense there in pure water. All right, so now instead of thinking about the different types of acid-base theories, let's just understand that when it comes to pH calculations, right, here's an aqueous solution, I want to know what its pH is. All it matters is what I added to solution. What I added to the water, is it going to increase the amount of H plus, or is it going to increase the amount of OH minus? Or is it not going to affect the amount of H plus or OH minus, right? If it's something that I add to water that doesn't affect the amount of H plus that's in the solution or the amount of OH minus that's in solution, then that substance is going to be neutral, okay? But if what I add to water increases the amount of H plus, that's going to be an acid. If what I add to water increases the amount of OH minus, that's going to be a base. But understand, in pure water, this reaction always has to reach an equilibrium. So now we got to think about an acid as something that causes the H plus concentration to increase, but at the same time, it's causing the OH minus concentration to decrease. And increase or decrease around what? Well, the starting point is 1 times 10 to the negative 7, right? In pure water, when we start out with just H2O liquid, this is the amount of H plus, and that is also the amount of OH minus. An acid is something that's going to drive the concentration of H plus above this number, but at the same time, it's going to drive the concentration of OH minus below this number. Because the molarity of this times the molarity of that always has to be 1 times 10 to the negative 14 in a water-based solution. So as H plus increases, OH minus decreases, and vice versa. So a base is something where if I add to water, it's going to drive up the concentration of OH minus, but at the same time, it's going to be driving down the concentration of H plus. And remember, the starting point for both is 1 times 10 to the negative 7. So if my H plus concentration is above 1 times 10 to the negative 7, I'm going to have an acid solution, and my pH is going to be below 7. If my H plus concentration is below 1 times 10 to the negative 7, then I'm going to have a basic solution, because when I do the negative log, it's going to be above 7. All right. So the product of these two concentrations, no matter what I've added to my solution, if it's water-based, then this system has to reach equilibrium, and that equilibrium position at 25 degrees Celsius is 1 times 10 to the negative 14, right? So the concentration of H plus times the concentration of OH minus in any water-based system, water-based solution, that concentration will always be, the product of those two concentrations will always be Kw, 1 times 10 to the negative 14, all right? So again, an acid is something that's making this go up and at the same time making this go down, right? And a base is making this go up and at the same time making this go down, okay? So if H plus increases above 1 times 10 to the negative 7, then OH minus is going to have to decrease so that the product of these two is equal to 1 times 10 to the negative 14, all right? So a base would be the opposite. A base is something when I add to water, it's driving up the concentration of hydroxide, but also, at the same time, that means it's driving down the concentration of H plus from 1 times 10 to the negative 7. Remember, the molarity of H plus and the molarity of OH minus in pure water is starting at 1 times 10 to the negative 7. So that's our starting point for those concentrations. And a base is something that when I add to the water is going to make the concentration of hydroxide greater than 1 times 10 to the negative 7. But again, this always has to be true right here in a water-based system. So as this goes up, this is going to have to go down to maintain that equilibrium position, that KW. All right. So why is HCl an acid? Well, we can show it like this. That's the Arrhenius acid. Okay. When I put it in water, I get H plus ions. Okay. But this reaction kind of shows it as an Arrhenius or a Bronsted-Lowry. It's a proton donor, right? You add it to water, you get hydronium, right? Because it's donating its H plus, its proton, to H2O. All right. But when I add it to water, it's producing this or it's producing that. So it's going to be increasing the concentration of hydronium or H plus above this point. Okay. So why is sodium hydroxide a base? Well, when I dissolve the salt in water, what do I get? I get hydroxide ions. So by adding this to water, I'm going to be increasing the amount of hydroxide I have in solution, and at the same time decreasing the amount of H plus in my solution, because the equilibrium position for the product of those two is always 1 times 10 to the negative 14. All right. So if I increase my concentration of OH minus above this number, then I'm going to decrease my H plus concentration below this number. Okay. All right. So these equations you need to have, I mean, they're on your formula sheet, but they should just be like the back of your hand, right? So pH is the negative log of H plus, molarity, or hydronium. It really depends on how you're given the question. So just understand that that's synonymous with that. And remember, brackets means molarity. So if I know the molarity of H plus, I take the negative log of that, and that's the pH. If I know the molarity of OH minus, I take the negative log of that, that's the POH. And if I know one, I know the other because I know that pH plus POH always equals 14, right? And I also know that the OH minus concentration times the H plus concentration always equals 1 times 10 to the negative 14. So again, if you know the pH or you know the POH, or you know the H plus concentration, or you know the OH minus concentration, you know all of them. You can calculate all of those numbers. If I know OH minus, I can figure out the H plus concentration, right? If I know OH minus, I can figure out the POH, but then I can use this to find the pH, right? Or I could use KW equals H plus times OH minus to find, given H plus, to find hydroxide, or given hydroxide molarity, find H plus, right? So given one of those little values, pH value, an OH minus concentration, an H plus concentration, a hydronium concentration, you can calculate all those things, right? And again, all of this right here, so this is always true, these equations. But this equation right here, pH plus POH always equal 14, that's only true at 25 degrees Celsius. All right, that number would change as KW changes. Okay, because all P means is you take the negative log. So if you take the negative log of KW, you get 14. Okay, and that's where that number comes from. Okay. So how do we calculate the pH of a strong acid solution? So first we have to know what acids are strong acids. So here are kind of the 6 common strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, and perchloric acid. Now, a lot of times we're going to throw in this is perchloric and this is chloric acid. Sometimes this is not included in the list of strong acids, but sometimes it is, and we're going to just include it. So we're going to say, like we always say, there's 7 diatomics. We're going to say there's 7 strong acids. So here's our 7 strong acids. Note that HSO4 minus is weak. So when we see H2SO4, it completely disassociates, but it's only the first H plus that dissociates. So all of H2SO4 in solution will become one H plus ion and then this ion, HSO4 minus. But this ion won't 100% dissociate. Okay. So what do we need to know about strong acids? If you have a strong acid solution and you know the molarity of the acid, that's an easy calculation, because the molarity of the acid is the molarity of H plus. Okay? So if you have a strong acid and you know its molarity, if you have a strong acid solution and you know its molarity, the molarity of the acid, so if I was told the molarity of HCl, that molarity is the molarity of H plus. because the definition of a strong acid is it completely dissociates in water. So if I start out with 100 HCl's, I'm really in water, I'm really going to end up with 100 H pluses and 100 Cl minuses and 0 HCl's still together. So if you're given the strong acid, the molarity of the acid is the molarity of H plus. So if you want to calculate the pH of a strong acid solution, it's just the negative log of the acid concentration, okay? So if you're told you have a 0.1 molar solution of HBr, well, guess what? You have a 0.1 molar solution of H plus, because that's a strong acid, and the molarity of the acid, 0.1 molar, is the molarity of H plus. So all we would have to do is take the negative log of that concentration, knowing that that represents the concentration of H plus in my solution, and we get a pH of 1, okay? So you're given the concentration of H2SO4 is 0.0035. Well, if we recognize that as a strong acid, and we gotta be careful, don't double the H plus concentration, because it's only the first proton that completely dissociates. Now, to completely neutralize this acid, I gotta take out all of the H pluses. So I would need 2 moles of hydroxide for every 1 mole of this acid. But when it comes to the amount of H plus I actually have in solution, it's only the first proton that dissociates. So the molarity of this is the molarity of H plus or hydronium in my solution. So if I take the negative log of that, I get my pH, okay? And the reason I can just go straight to, I was given the molarity of the acid, so that's the molarity of H3O plus, because it's strong, okay? The molarity of a strong acid is the molarity of H plus, all right? And then also think about it, remember, right? If we knew that was the molarity of hydronium in our solution, then we should be able to calculate the concentration of hydroxide. Now, it's really not something that's a common question that you would really care about, but if you understand acid-base theory, it would be a question that you could be asked to see if you truly understand your acid-base theory. So you're given the concentration of a strong acid, you know that's the concentration of hydronium, and then you understand that, well, this is a lot bigger than 1 times 10 to the negative 7. And remember, that's our starting point. 1 times 10 to the negative 7 is our starting point for hydronium and hydroxide in any water-based solution. That's our starting point. So as the H plus concentration went well above 1 times 10 to the negative 7, that means the OH minus concentration is going well below 1 times 10 to the negative 7. And so we could just throw in our hydronium concentration into our Kw equation. And if I was given hydronium, I could solve for hydroxide because I could plug in Kw. Kw is 1 times 10 to the negative 14. So if I go 1 times 10 to the negative 14 divided by our H plus concentration, that'll give me my hydroxide concentration. So in that sulfuric acid solution, that's the molarity of hydronium, that's the molarity of hydroxide. Notice it's well below 1 times 10 to the negative 7, right? All right, so strong base, we really don't have strong bases like we have strong acids. Strong bases are just hydroxide salts. So now, because notice a strong acid, when it dissociates, it starts out aqueous. It's the question, so like HCl, it starts out in your solution as dissolved in water, HCl aqueous. The question is it HCl together, surrounded by water, or did it dissociate and form H plus and Cl minus, okay? And if it 100% dissociates, it's a strong acid. But a strong base doesn't start out aqueous. It starts out as a solid salt, so sodium hydroxide, lithium hydroxide, right? Metallic hydroxides could be considered strong acids because if it does dissolve, you get an OH minus. If magnesium hydroxide dissolves, you get 2 hydroxides, right? For every 1 mole of magnesium hydroxide that dissolves, you get 2 moles of hydroxide. For every 1 mole of aluminum hydroxide to dissolve, you get 3 moles of hydroxide. So to figure out the pH of a strong base solution, you need to know the molarity of hydroxide. You can, if you find the molarity of hydroxide, you can take the negative log of that, and you can take the negative log of that and get the POH and then subtract from 14. But really, if you have this, then if you have a saturated solution of these salts, then you would need to know their KSP values so you could figure out the hydroxide concentration when it's saturated, and then you could find the POH and then subtract from 14 to find the pH, right? But if you're given the molarity of an ionic hydroxide, so a salt that contains hydroxide, to get the molarity of hydroxide, all you have to do is multiply by the subscript of hydroxide. So if I was told I had a 1 molar solution of sodium hydroxide, remember, when a salt dissolves, it means it dissociated automatically. So 1 mole of this in solution, if you're told NaOH aqueous, well, that means Na plus ions and OH minus ions. So if I was given 0.1 molar NaOH aqueous, that's 0.1 molar hydroxide. If I was told I have an aqueous solution of aluminum hydroxide, and this was the molarity of the aluminum hydroxide, if I took this times 3, that would be the molarity of hydroxide. And again, once I know the molarity of hydroxide, case closed. I can find the POH, I can find the pH, I can find the hydronium concentration, whatever you want, right? So negative log of this minus 14 would give me the pH. Negative log of this minus 14 would give me the pH, okay? You could just stop at the POH sometimes, but a lot of times questions will ask you about the pH, not the POH, just because pH is more common, okay? All right, so what about a weak acid, all right? So here's the deal, and we're gonna like label a monoprotic. Monoprotic means an acid that only has one H plus, okay? We're gonna label a monoprotic weak acid as HA, right? H plus paired up with an anion. Okay, and the deal is the concentration of HA, if it's a weak acid, is not the concentration of H plus. Okay, so if you're given the concentration of HF, that is not, if you're told you have a 0.1 molar solution of HF, that is not the molarity of H plus. If you're given a 0.1 molar solution of HCl, that is the molarity of H plus because HCl is strong, but it's not for HF because HF is weak. All right, so this reaction's happening, but notice that this reaction is not going to completion. It's reaching an equilibrium. So what does that mean? It means all of the HF does not dissociate. All of the HF does not react, okay? So in order to actually solve for the pH of a weak acid solution, you need to know the concentration of the acid, but then you need to know the Ka of the acid. Because what we need to do is figure out the equilibrium concentration of H3O plus. So remember, Ka would be the equilibrium constant for this reaction, an acid acting like an acid with water, meaning donating a proton to water. So the equilibrium constant for this process would be the Ka of HF. So if we know the equilibrium position of this reaction and the initial molarity of HF, we can figure out the pH of solution, all right? It's just a simple Rice chart. So let's say we're given a 0.1 molar solution of HF, and we got to recognize that that is not the molarity of H plus because this is a weak acid, okay? And we're told the Ka is 2.4 times 10 to the negative 6, all right? So Ka would be equal to this expression. It's the equilibrium constant for that reaction, and we know what it's equal to. If we made a Rice chart, the HF would start at 0.1, we'd lose X, and at equilibrium it would be 0.1 minus X. We'd start out with 0 hydronium and 0 F minus. Okay, now maybe what you're thinking is, do we really start out with 0 hydronium? No, we start out with 1 times 10 to the negative 7, but that's really small, so 0, okay? And we get X and X, all right? So at equilibrium, Ka of the weak acid, which we were given, is equal to X times X over 0.1 minus X, okay? So what we would do is 5% rule this, right? We would say 0.1 minus X is really going to be close to 0.1, so we'd 5% rule. So we get this simplification. So we get Ka equals X squared over 0.1, and that 0.1 was the initial concentration of the HF. And so if we solve for X, X will be our H3O plus concentration, and the negative log of X will be our pH. So we solve for X, take the negative log of that, that gives us our pH. So let's think about it. If I had 0.1 molar HCl, the pH of that would be 1, the negative log of 0.1. But if I have 0.1 molar HF, look at the pH, it's only 3.3. That's the difference between a weak acid and a strong acid. A weak acid, you don't get as much H plus for your money, right? A strong acid, all of the acid becomes H plus, okay? All right. So here's our weak acid shortcut. If you have a weak acid at equilibrium and you're trying to find the pH, you can do this shortcut. So it would always, if you make and this is if it's monoprotic, so just one H plus. If you make a race chart, it'll always come out to be Ka equals X squared over the initial concentration minus X. And it will 5% rule that minus X right there. And so really what we get is our shortcut is Ka equals X squared over the concentration, the initial concentration of our weak acid. And understand what X represents in the shortcut. X represents the hydronium concentration, but it would also represent the A minus concentration, okay? Right, because, you know, like here, you get, if this was HA and not HF, you would get hydronium and A minus, okay? So, and notice that it's a 1-to-1 ratio all the time, so X and X, so that's where that X squared comes from. And so, X would be the concentration of hydronium. It would also equal the A minus concentration, but also the negative log of X would give you your pH, okay? So if you know the Ka, you know the initial concentration, you solve for X, the negative log of X is the pH, all right? We can do the same thing with a weak base. A weak base shortcut would always end up with this. If we set up our Rice chart, we'd end up with X squared over the initial concentration of the base minus X. We'd 5% rule that X, and we get the shortcut. But you have to understand, if it's a Kb shortcut, because you have a weak base, X does not equal hydronium, X equals hydroxide. It also equals the conjugate acid, which we'll talk about, of the base, okay? Which is kind of like A minus for the acid shortcut, okay? But X equals the hydroxide ion concentration, so the negative log of X in this case does not equal the pH, it equals the POH. But a lot of times you're asked for the pH instead of the POH, so we do 14 minus the negative log of X. So 14 minus the POH would give us our pH, okay? So I know that's a lot, but essentially if you understand this, then you'll be able to really roll with all the calculations we end up doing for the rest of this unit, okay? We have some more complicated things to come, okay? But if you understand those concepts there, you're in really good shape, and you know, you should be able to do your 5-1 assignment for all the acid-base theories, but now you should be able to do the 5-2. Okay, the 5-2 is just our acid-base calculations, and that's really what I just went over. All right, so we'll do a lot of practice in class. We'll go over all the notes and stuff in class, but I just wanted to give you kind of an intro on that stuff. All right, have a good one.